Hey, welcome back everyone to session number 4 on Sysmac Studio. This is our final educational session. There will be one more session next week that's optional. If you guys want to hop on and talk Sysmac, you can, but it is optional. So for this session, we will be going over networking and communications in Sysmac Studio. So networking ability is a very strong part of Sysmac Studio. We play well with most third-party equipment. We support a lot of different protocols. And today we're going to be going over some of the more common ones and ones that I can easily demonstrate on a Teams meeting. Not much point in me sending service data messages to an EtherCAT servo drive. That's not something that you guys can really replicate. Now, when I'm going through Sysmac, you guys are more than welcome to play along so you have an example. That being said, I will be sending out an example project after this that has code examples for everything that I've demonstrated today. So it's going to have all of the code needed to explicit message PLC and get a variable by tag name. So in the future, if you needed to do that, you could reference this example program, and all you would really need to do is change the target IP address and the tag name, and you should have ready to go code essentially, or at least a good point of reference. So let's get rolling. So on the agenda, we're going to talk a little bit about the protocols that we support. Then we will dive into Ethernet IP. So we're going to spend a fair bit of time on Ethernet IP since it is the most common industrial network today, at least in North America. Then we'll go over some examples. I've got some hardware here that I'll be establishing Ethernet IP connections with, both implicit and explicit connections. Then we'll talk a little bit about OPC UA, and there's a free software tool that we can use to demonstrate OPC UA capabilities. And when you set it up with SCADA software, it's very similar to how we'll be setting it up with a piece of software called UA Expert. Now, Modbus is a classic protocol, and we support it natively with our PLCs, both TCP, and if you have a serial interface, we do RTU as well. I will be doing TCP today. And then finally, we'll kind of wrap things up with a communication comparison and summary of the various protocols that we covered today. So in our Sysmac line, we have NJ and NX PLCs. So the NJs, which is the PLC pictured here, they can actually accept CJ cards. CJ PLCs are one of our previous lines. And there's a lot of legacy protocol support in there, and a lot of specific protocols like Profibus, Profinet, DeviceNet, CompoNet, and CANopen. We also have a card called the protocol macro card, which this list on the right-hand side here are just the default protocols that you can do with the protocol macro card. So you might have a very specific piece of hardware, like an older E5 temperature controller, and you need to talk to it. Well, we've got a protocol built into the protocol macro portion of it. So now the NJ and NX, the protocols that they can do that they have in common are EtherCAT and Ethernet IP. So these have Ethernet and EtherCAT ports on all NJ and NX CPUs, and the protocols themselves are embedded much deeper. So they essentially run in the background and they manage the connection. They alert you of any problems. And in the case of Ethernet IP, it's even a self-healing network. So they're very core protocols, EtherCAT and Ethernet IP. The rest of these reside on a different application layer. Well, some of them do, but we do MQTT with our PLCs. So this is a very common protocol these days. It's gaining popularity. We can do Modbus TCP and Modbus RTU. These are protocols that we have to program logically to do, where a lot of these we actually configure in a much different section of the PLC, and I'll be walking us through how we do both of those types of protocols. IO Link is something we're pretty heavily invested in. So we have cards that can do IO Link, and we have masters over Ethernet IP or EtherCAT that we can get the IO Link data from. OPC UA and SQL are embedded protocols. So these are running in the background of our PLCs, and it doesn't really take away from your PLC performance since it's running on multiple cores. And then Ethernet and serial ASCII type communications, so socket communications, these are commonly called. We still occasionally run into a device that has essentially its own protocol. You have to send it an ASCII string and it replies with an ASCII string, and you have to parse that data when you get it back, and you have to send it the ASCII characters according to what it's expecting. So we still support those, and they're fairly easy to implement in the PLC still. Now, Ethernet IP is going to take up a good chunk of this presentation today. So it's a very commonly used high-level communication protocol. So a good example would be controller to controller communications or controller to visualization type communications. But due to its kind of widespread availability and development, we also see it on the device level network, which is where we typically use EtherCAT in a lot of our configurations. Ethernet IP is fairly versatile. We're not going to dive too much into the advantages or disadvantages of one versus the other. If you want to come on the session next week, we can take a bit of a deep dive into it. If you're on the fence about which one to choose for an application, we can talk more about it. But Ethernet IP is essentially everywhere, and it spans both the device level and the data level. So we're very on board with it. We support it. We're a member of the ODVA, and we have members on the board of the ODVA that manage the protocol itself. So we're very invested in it, and it's not going anywhere anytime soon. Now, Ethernet IP essentially has two types of communications. So implicit and explicit type communications. So implicit is a tag data link, it's commonly known as. It's commonly used if you were to, for example, have a remote I/O rack and your PLC communicated with it at a predetermined RPI or requested packet interval. So you got that data from your inputs and you wrote data to your outputs at, let's say, a 15 millisecond interval. And this data happens regularly. There's no need to change it. You're getting all the data you need. Now, explicit messaging is something where you're actually telling programmatically, you're telling the PLC which address in the Ethernet IP device that you're going after. So there are things called class, instance, and attribute values in explicit messaging. They're comparable to a Modbus address, just 3 sections instead of 1. Now, we'll be doing examples of both of these, but explicit we generally use for less commonly written to or read from data. If we're sticking with the example of remote I/O, you might want to pull the current consumption of an input card. That's not something you generally want every single communication cycle. You might just want to check that once every few minutes. Lots of different examples out there, but those are the two flavors of Ethernet IP messaging. So implicit runs at the core of our controller. The controller manages it. We set it and we forget it, and it exchanges data, updates the variables in our PLC. We don't deal with it. Explicit, we have to execute function blocks to send this data. We have to receive that data, make sure its integrity is there, we didn't get any errors, and then we have to deal with that data accordingly. Now, there are a couple different ways we can explicit message. I mentioned the class, instance, attribute type explicit messaging. And this is something you commonly see in adapter class devices, which VFD would be a good example. So these have address values, but when we're dealing with a scanner to a scanner class device, which is generally a PLC to a PLC, it could be a PLC to a robot controller, but they support something commonly known as tag-based explicit messaging. So instead of specifying an address, we can actually specify the name of a tag in a tag-based PLC, and we can just read that tag by tag name, and it simplifies getting that data, not having to assign addresses to variables, that kind of thing. So we're going to have a quick demo of this. So I have a third-party PLC sitting next to me here, and I will open up Sysmac here. So in our logic, There are a couple different instructions for explicit messaging devices over Ethernet IP. Just give me a second here. I need to open up a second Sysmac project while I'm doing this. So UCMM, and this is part of the CIP spec naming convention. This is an instruction we use when we want to get to a piece of data by the class, instance, and attribute value of that data. So we see this in VFDs a lot. We see this in remote I/O racks a lot. Most adapter class devices will have class, instance, and attribute type values associated with their data. Now, there's another flavor of explicit messaging, we'll call it, and that is for tag-based, which is typically controller to controller, like I mentioned, and the CIP, send, read, and write instructions are what we use when we want to do tag-based explicit messaging. Hold tight here. I'm just opening up a project on my other screen here. Now, I mentioned that anytime we're explicit messaging, this is something that we have to do in our logic. So we trigger this. We might want to trigger it once a second. We might want to trigger it as fast as we can. But compared with implicit messaging, that's all managed behind the scenes. Explicit messaging, we have to set that up in our controller. So we're going to be using the CIP UCMM read in this case. So I'm going to grab the CIP UCMM read instruction, drop it on a rung. Now this instruction does require no special data types. So when we're dealing with class, instance, attribute type explicit messaging, we have to dive into complex data types, but this one is fairly straightforward. So the CIP UCMM read, we triggered this block with, I'm just going to use a simple contact to get the Rockwell tag. We need to name our function block, of course. I'll zoom in a little bit for you guys here. Now, the route path is probably the most confusing part of Ethernet IP explicit messaging. The route path, if you're unfamiliar with it, essentially tells the message where to go. So this can be quite a long string value. We can tunnel this through different PLCs if we want to go in one PLC's Ethernet port, out a different Ethernet port to a different network. We can actually get quite complicated route paths set up if we need to span networks and even span controllers. Fortunately, though, this PLC is on the same network that I'm on. So the route path for this, and this will be in the example project. Don't worry, you don't need to memorize this, but O2 sends this out our Ethernet port on our PLC, port 1, backslash, and then the target IP address of the PLC we're going after, which is 192.168.250.12. And then this last portion of the route path is specific to the PLC that I'm messaging. So it will be outlined in their manual, but you'll also have an example in this manual. So 01 is their interface, and \pound 00 is how we get to their CPU, which is where this global variable resides. So like I said, the route path is probably the most complex portion of explicit messaging, but you guys will have an example that you can reference in the future. And 95% of the time, you can just cut and paste from that example and you'll have a valid route path to work with. Timeout. We don't want to wait forever for this and keep that port open. So we give it a value for a timeout. 25 should be fine. It's 25 milliseconds. Now the source data is the name of the tag in the PLC that we're going to. Now, if you remember from the PowerPoint, the tag is called my real var, and it's a real data type. So data types are important, and our PLCs do care about the data type. So we do need to make sure that the tag name matches and the data type matches, or else we will get an error on this instruction. So the source data is the source variable name in the other PLC. And if you want to hard code a string, we do it with single quotations. And it was my real var. Helps if you spell it right. Now the size, this pertains primarily to reading arrays. So since we're not reading an array, our size is just going to be 1. If we were going after an array, and we can specify an array index in the tag name as well, if we didn't want to start at 0, we could actually start at index 15 and read 15 indexes from that array. So it is fairly versatile in that sense. But our size will be 1. Now the DST data, which is the read data, you can see this accepts any data type. And what we need to make sure here is that this data type matches the data type in the controller that we're trying to read. So it is a real, so I'll call it my NX real. And it's going to ask me which data type I want to make it, so I'll choose real. All of the other parameters on this are optional, but we can see how many bytes back that we received. If we have any errors, we can put some variables there to give us some troubleshooting information. And finally, I'll just put an output here to indicate CIP success. So that is all we have to do to read from a tag in another PLC. So I'm going to synchronize this project with my PLC and we'll test it out. Now in the other PLC, the variable is just incrementing based off a timer. So we should be able to see it change as we're going along here. It seems it's fine. Okay, let's check the project for errors before we transfer it. It's always a good idea. Had some leftover stuff from some testing I was doing earlier there. Okay. No errors, so we can transfer to the PLC. Okay, so we're up and running. We've got this logic running in the CPU. So when I flip this bit, if I didn't make any mistakes, I should get that real value from the other PLC. So the block executed successfully, and you'll see every time I execute this, that real, my NX real variable that I created is getting the value from my real var in the target PLC. So you can see a change there. So that is tag-based explicit messaging. It's a lot easier when you can use it because you don't have to specify class, instance, attribute, service code type information. We can do that. It's not a problem. It's just a different instruction and a different type of explicit messaging. So whenever we're dealing scanner class to scanner class device, this is usually the easiest way to do it. So any questions on explicit messaging? I know you guys don't have the hardware in front of you, so this is going to be a bit of a watch Stuart play with things session. But if you have any questions on Ethernet IP explicit messaging, that would be a good time before we move on. Okay, so that was our third-party tag-based explicit messaging. Implicit messaging is something that's a lot more common, and I'm sure a lot of you are more familiar with implicit messaging. So implicit messaging is Ethernet IP communications that are handled essentially behind the scenes. We tell our PLC the target IP address, the instance, the data size, that kind of thing. And our PLC will maintain that communication link with that device. It will constantly update that data. And if we were to ever lose connection with that device, there are system bits that we can look at that will indicate a connection failure. And if that connection's ever restored, it's self-healing, and that data will resume once the connection's restored. So what I have in front of me is one of our intelligent power supplies. So it has Ethernet IP and Modbus TCP abilities built in. So we can pull from this things like the current voltage, the current output, the lifetime remaining before replacement, any kind of, there's a number of different alarm bits. So generally when we're setting up an implicit connection, there are two things that we require. So one of them being the EDS file of the device. EDS is an electronic data sheet, and that will tell the PLC what instances it has available, the data sizes of those instances, and RPI limitations that it might encounter. So the other thing is the manual. So the EDS file will tell us where to get the data, but the manual will tell us what that data means. So I've got the manual open here for our S8VKX power supply. And it's got two sections, one for Modbus, one for Ethernet IP. So if we drill into the Ethernet IP section, we can go to the tag data link section, which is for implicit connections. And we can see essentially our memory allocation. So this is the instance we need, 100. It's 20 bytes in size. And those bytes are allocated as followed. So the first word, or the first 2 bytes, is a status word, and then we have our output voltage, our output current, peak hold current, years until replacement, et cetera, et cetera. So I could pull this as raw data if I wanted to. If I just wanted to use an array of 20 bytes, that will work just fine. That connection will be healthy. But then I need to take those bytes and I need to map them into all of these variables, because they'll be a little scrambled. If you've ever looked at a real value, for example, in byte form, it doesn't make much sense. So if you remember from last session, I mentioned that structures are something we can use in communications to make our life a lot easier. So I actually have in my Sysmac project, and I'll include kind of our structures master file, so you'll have structures for anything Omron. But I have made a data type ahead of time for the S8VKX, and this matches what you just saw in the manual to the bit level. So if we use a variable of this structure, and this structure matches what's in the manual, the data map of the device, then our PLC is going to break apart all of this data for us, and it's going to map it into these variables, and it's going to save us a lot of time when we're parsing out this data. We don't have to do that anymore. It's done for us, essentially. So first thing I'll do is I'm going to make a variable of this data type, the S8VKX data type. So I'll create a new variable, and this will be my, we'll call it power supply EIP input. The data type will be that structure that I just showed you, the S8VKX data structure. And now for the network publish column, this is something I've referred to a few times and said we'll talk about this on the communications class. So for Ethernet IP, tag data links can either be an input or an output. In the case of this power supply, there is no output that we send to the power supply. We're just monitoring it. So this is only going to have an input variable. If this were a VFD, chances are it would have an input and an output data link that we would have to make variables for. But I chose this just to keep things quick. So there's our variable that we'll use for Ethernet IP. It's set as an input for the network publish. Now, since Ethernet IP is managed behind the scenes, it has its own special setup area. So in our tools category, if we go to Ethernet IP connection settings, we can pick the port which we want to configure. We can have both ports support Ethernet IP. And if we had cards on our PLC that supported Ethernet IP, they would be listed there as well. But once we're in here, we have two categories essentially. So our tag sets and our connections. So first thing we do is after we've made our tag, I'm going to click on registration all, and that will scan my global variables for any tag that has the input or output network publish trait modified. And it's detected my power supply input tag that I made. So I'm just going to go ahead and click register. And now it's an input variable for Ethernet IP. I don't have any output variables because we didn't create any. So there's my variable, and you can see it's 20 bytes in size. So it matches the data that the power supply is making available to us. If that data size doesn't match exactly, then the connection will fault out. So it's important that this size matches what's in the documentation for the device. Now in the connections tab, this is where we establish the actual connection. So Omron in Sysmac Studio, we have preloaded all EDS files for every Omron device. If this were a third-party device, we can simply right-click over here and display the EDS library. I think I may have said ESI there, but ESI is for EtherCAT, EDS is for Ethernet IP. So you can see I have some third-party ones in here, and we have a lot of Omron ones in here as well. So I'll add a target device first. So we click the plus sign at the bottom of the target device window, and we'll enter the IP address of the target device, and my power supply is .10. Now in the model name category, we're going to pick the S8VKX. So we'll scroll down to it, and we have a lot of different model numbers. So give me a second to glance over at my power supply here, make sure I pick the right one. So I have an 09024A, which is right here. And if there were multiple revisions, we would have to pick the revision that matched the device. Usually there is only one revision. So we'll click add, and now we have this target device in our project, and we can add it to our connection setup window here. So we'll hit the plus sign, and from the drop down, this will display all target devices that we've set up. Now it knows that 100 is the instance that we're going after, which if you remember the manual here, that's correct. This is instance 100, and it's 20 bytes in size. So this knows that instance 100 is 20 bytes in size. It gets that from the EDS file. And now when we pick the variable here, this will detect any input tag that matches that size. So if you hit this drop down and you don't see your tag, then it would be because your size does not match. So there's the tag we created, and the default RPI it's not happy with. We don't need 50 millisecond update time from our power supplies, so I'm just going to give this 200 millisecond update time. So every 200 milliseconds, we are going to request this data. And then the timeout category here. So if the RPI times 4 passes and we don't get a reply, so that would be 200 milliseconds times 4 elapses and we don't get a reply, then we will trigger an alarm on one of the system bits that we could use for troubleshooting. So that's all set up. So I'll go online with my PLC. And I will transfer this to the controller. Now we could have done this as an online edit, just to be clear. We can edit our global variables. Or I should say, we can add global variables online, and we can edit Ethernet IP connections online. It's just a little easier to do it all at once. So I've synchronized with the PLC. Now I'll transfer my Ethernet IP configuration to the controller. And we're done. So to tell if this connection is actually successful, because this device might not even be there, we don't know yet, we could throw that variable in our watch tab and see if we actually have live data from it, which we do. You can see we've got a couple of our bits are true. You can see there's our output voltage right there, 24.2 volts. So that's a pretty good indication we have a healthy connection. Another place we can look is something called the monitor feature for Ethernet IP. So if we right click on this port, we can monitor it. And there's .10, which is our power supply, and it's blue. So if that were red, we would have a connection problem. And if that were red, we could also drill into that a bit more and get the error status from it and work on troubleshooting that way. But that connection was successful. And I'll just, to demonstrate here, take a screwdriver and adjust my output voltage on the power supply, and you should see where my mouse is on the screen. You should see that change by a volt or so. $23 now. Now we're up around 24.4. So those are implicit connections. I didn't write any code. This is all being managed behind the scenes by the PLC. And if we wanted to, we could reference system bits to indicate if that connection is healthy or not. So any questions on implicit connections? Okay. And again, just a reminder, there will be an example program sent out that has basically everything we cover today in it. So a great reference for future use. So I'll go back offline and we'll switch back over to PowerPoint here. So OPC UA is a protocol that most of the NJ and NX PLCs support. Some models don't, most of them do. If it's something you need, a lot of them have it out of the box. Some of them you have to pick a specific model, but the NX102 and the NX5 all have it out of the box. But it's essentially a client-server based communication protocol. It's gone through a couple of revisions over the years. It's actually fairly old, at least the initial implementation was. But it has a lot of advantages, and we see it a lot in SCADA. So most SCADA software has a client built into it, and our PLC can be the server in this situation. OPC UA is something that runs behind the scenes, similar to the implicit connection that we just made. And luckily, the majority of the setup for OPC UA is actually done on the client side. On the server side, there's not a whole lot we need to do besides enabling it. So on our PLC, it supports OPC UA. This is an NX102. And in our Multi-View Explorer, there's a category here called OPC UA settings. And all we have to do to get it enabled is change the OPC UA server setting to use. It's set to do not use by default, so we change it to use. If you needed a custom endpoint, you could give it a custom port. I'm just going to stick with 4840 since that's the standard for OPC UA. And if we have an SD card in our PLC, we can actually record our execution log. So if you're getting into encryption and multiple connections and you're running into some issues, we can actually go through this log. It's plain text, and we can see that this user attempted to make a connection, but their certificate was invalid, or they used the incorrect password, something like that. So it can be useful for troubleshooting. For what we'll be doing today, we're not even diving into authentication or usernames and password. It's just going to be an unencrypted, unauthenticated connection, and we're just going to read the tags in the PLC. So we've set it to use. Now, once our server's enabled, and we will have to do a power cycle, but we can do that from Sysmac. Once that's enabled, variables that are now available over OPC UA are variables that have the network publish column set to publish only. So I'll change a few of these to publish only. I'll make a couple copies of this one. It's not just elementary data types either. We support structures, we support arrays. But anything with the publish only set on it will be available for OPC UA. So I'll transfer this to the PLC now. And we should get a pop-up that we need to reset the PLC to fully enable OPC UA once we're done synchronizing here. There it is. So we'll hit OK, and I can simply just put the PLC in program mode, and I can reset the controller from the controller menu without having to go find the fuse for it, kind of thing. So I'll give that a second to reboot, and in the meantime, I'm going to open up the OPC UA client software. So UA Expert, or Unified Automation Expert, is essentially a testing tool for OPC UA. So this will let us pull tags from OPC UA servers. This acts as a client. So we'll come back to that. PLC should be rebooted now. So I'll go back online. Might have been a bit premature. There we go. And now in our OPC UA, if we right click on the server, we have a couple different options when we're online. So in security settings, I'm going to allow no security policy, and I'm going to permit an anonymous logon. This is just to keep things short and sweet for the demo here. I have done, without too much difficulty, full 256 SHA encryption with OPC UA, where you have to generate certificates, register certificates. So it can be quite secure, or it can be anonymous login with no encryption at all. So I'm just going to allow that for now for the purpose of this demo. So we'll transfer those security settings, and now we should be able to find this with our UA Expert software. So I will add a server. And here we have where we would set up our encryption here. So we can have our certificates and private keys. We can have username and password, or we can have anonymous. So I'm just sticking with anonymous. And the endpoint is going to be opc.tcp. So it's warning me that there's no valid certificate. That's okay. I'm just going to tell it to trust it temporarily for this session. So we're connected now with OPC UA to the PLC. And now one thing we can do with OPC UA that is very convenient for a SCADA type application is we can just tell the OPC UA server to send us a list of the tags that you have available. Some of you may have worked on HMIs or SCADA systems where you had to export a database from a PLC, modify it in Excel to be in the right format, and then import it into your SCADA software, and then create all the variables for it. Well, with OPC UA, we can actually just drill down to the global variables here. Hopefully that's big enough for you guys to see. I don't think I can zoom on this software, no. But here are all of the global variables that have the network publish attribute enabled on them. So SCADA software and visualization software can pull this list from your PLC. When you're making an object, you can just choose the variable from this list generally, and that can make your life a lot easier. Just kind of go side by side here so you can see the list. So everything with input, output, or publish on it is in this list here. Hopefully it's big enough for you guys to see. But so that's OPC UA, a very quick demo of how we pull the tag list from the controller and work with it. I'm just going to close out of that. Are there any questions on OPC UA?
Yeah, can you hear me?
Yeah, I can hear you, Tom.
I was just wondering, you just mentioned that anything with the input, output, or publish only in our variable list, that'll be seen by the UA client there?
Yes, correct.
Okay, so I don't have to duplicate any variables, so I can have one in my PLC and one on the server.
Yep, exactly.
Okay, perfect, yeah.
And you may have noticed, or you may recall that this power supply Ethernet IP variable that we made is actually a structure. And the UA client detected that. So we can, and I'm not going to say every client can deal with structures properly, but a lot of the popular SCADA offerings can deal with structures directly. So yeah, we can save a lot of data mapping in some cases by dealing with the structures directly, right from the input variable as well.
Perfect, thank you.
Yep. Any other questions on OPC UA? Good. One thing I didn't talk about too much with OPC UA, and it's all part of the protocol standard, but this has a lot of advantages to protocols like Modbus or even Ethernet IP in some cases, because we can read and write data on certain updates. So with Modbus, which we'll be doing a demo of here next, I believe, we are going to ask for, in this case, 20 bytes from that power supply. And most of those bytes are going to be exactly the same as the last time we read those bytes. So it's kind of unnecessary overhead. It's unnecessary network traffic when we only really care to get fresh data once it's changed. So there are some implementations in OPC UA to assist with this. So we can actually, the PLC can actually let the client know when certain tags have a new value. So it can really clean up your network compared to Ethernet IP or Modbus. Great for SCADA applications. It's very good for cloud monitoring and SCADA. And that's what we just did. Now, Modbus TCP. Modbus is a classic protocol, been around for a long time. Very open. I'm sure most of you have heard of it. Most of you have probably worked with it. So we're going to go back to the power supply again with Modbus. So these support Modbus and Ethernet IP. It doesn't matter. You can pick one or the other. I can't say I've ever tried to do both at the same time. So what I'll do is I'm just going to delete the implicit connection that I have with our power supply. And I can just click on the garbage can, transfer that to the controller. We're going to do it in run mode so we don't have to shut down. And now I've deleted that take data link with the power supply. So for Modbus, I'm going to go offline just because it's a bit easier to do it. I'll even make a new section for Modbus here. Now, the Modbus functions are built into Sysmac. We used to have to use a library to do it, and I think even in the student material, I might have included that library. I've just been doing this for so many years that I kept the library in there even when we added it to Sysmac natively. So the Modbus functions are all built into our toolbox, and if we just search mod, it will pull up all of our Modbus instructions. So Modbus RTU is the serial-based Modbus, which we support with our serial cards. Modbus TCP, we can just use the default Ethernet port for. So if you recall from the manual, there's a section on Ethernet IP and a section on Modbus TCP. So Modbus TCP, I could do a whole session on the protocol itself, but it is a protocol that we have to program into our PLCs, and we have to sequence the messaging, the reads, the writes. We have to keep an eye on the socket to make sure it didn't disconnect, that kind of thing. So it's a much higher level protocol, and it does take a bit more programming. But essentially, Modbus operates with a function code which tells what kind of message it is. So function 3, for example, is read multiple registers. Function 6 is, I believe, a write. No, 10 is write multiple registers. And we actually support a operation command function code, which we're not going to deal with today. But essentially, we need an IP address, we need a unit ID, we need a function code, we need a data register address, and we need a data size for Modbus TCP. Now, this manual will tell us all of those, except the IP address, of course. We know what that is. But what we're looking for here is the data map. And there's our register address list. Now, fortunately, the address list in Modbus TCP is identical to that of Ethernet IP. So that structure that I was using for Ethernet IP, we can actually use that in Modbus TCP. We don't have to make a new structure for it. So the first thing we need to do with Modbus TCP, because it is a Ethernet socket ASCII-based protocol, is we will use a socket block, since we have to open a socket, SKT, sorry. So we have a block called socket TCP connect. So this will get our PLC to attempt to open a socket connection with a target device at a specified port. There are programming examples in the manual of what we're doing here as well, and there will be a Modbus example in the example program that I distribute. So it is a function block, so we'll give it a name. We'll call it the power supply socket. Now the source TCP port, if we use a value of 0, it's just going to take whatever available port it has on the PLC. If we wanted to specify a port, or if the device we're connecting to required you to have a certain port that you're connecting from, we could specify that port and we could use that port. But in Modbus, it generally doesn't care. It's the destination port that you need to go to. So the destination address, that's going to be the IP address of our power supply. So we will hard code that, which is 10. Now the destination TCP port This is in the manual, but the Modbus TCP default port is 502. So that's an unsigned integer. So I will hard code that as 502. Now this function block creates a variable called socket. And that is essentially the information that sequential function blocks will need to use this socket. Just the way that we pass that socket to another function block for communication purposes. So I'm just going to call this the power supply socket. I do want to have the ability to turn this on. And I do want to make sure that I can see when this socket is open and connected and ready. So the next thing we'll do is we have a couple different Modbus TCP function blocks. And if we just search mod, it'll bring up all of our Modbus stuff. So we have a TCP command, we have TCP read, and we have TCP write. To differentiate between them, command can be either a read or a write, or it can be a custom command. Some devices support custom function codes in Modbus. Since we're working off standard function codes and we're only going to be reading from this power supply, I'm just going to use the Modbus TCP read function block. So I'll make a rung below this. And I'll put a bit in there so that I can trigger a read. It's a function block, so we need to give it a name. Now, the first variable is a socket, and this socket connect block presents a socket variable to us. So that's how we actually use this socket with our Modbus block. So I'm going to give it the same variable name that we used up here, which is ps_socket. So now this will send all of the traffic from this block out out to 250.10 at port 502. Now, the unit identifier is something that some devices use, but most TCP devices don't. A lot of the time, it's just 255. This is something that they kind of carried over from Modbus RTU when Ethernet was developed. Some devices use it, some don't. This particular device does not use it, so specifying 255 in Modbus is generally what you do in TCP in that scenario. So our read command, our read data, and our timeout value. So the read data is where we're going to bring that data into in our PLC. The timeout is pretty self-explanatory, how many milliseconds we want to wait for a reply. And then is a complex variable. It's a structure. So it has more than one variable contained within it. So we'll create the variables for these remaining three fields here. Now the read data is what we're going to bring the data back into. So we want to make sure that it's big enough, either greater than or equal to the size of the data that we want to read. Now we do specify the quantity of data, and you don't need to read it all at the same time. But I would like to get it all with one message. So I'm going to make a word array that is 10 words long, which should give us 20 bytes, which is the size of the data that we want. So timeout, we'll just give it a value of 50. on these output parameters if we wanted to. I'll put the read size here. I will put an indication for an error. And I'll have an output on the rung to see if the communication was successful. And so I will first clear this error that I generated, and then I will go online and transfer to the PLC. And you see a red line next to the rung. This is a uSint, and I specified it as a uInt. So I'll make that a uSint. That should clear it. Almost. Okay. So warnings are okay, errors are not. We've got 0 errors, so we can transfer to the PLC. Okay, so before we test this, you may recall that the read command is a structure. Now, there are a lot of ways we can get to the members of that structure, but what I like to do in a scenario where I don't really need to modify them and I'm just testing things, we can actually add that variable to our watch tab page, which is view watch tab page table for structures. And we can put that ES read CMD in there. And this will show us, so this structure actually has 3 members. So it has the function code, it has the read address, and it has the read size. A lot of people like to put a structured text, embedded structured text routine above the block, just so you can see the mapping. For this, I'm just going to use the watch tab page table. So the function code that we want, if you remember from the manual, is, I'll go back up to it. So read multiple registers. That's one of the function codes it supports. So read holding registers is what we call that. So I'll change that in the watch tab page. Now the address, according to the manual, scroll back down to our data map here, starts at 0000. So that's good because that's what that variable value is. And now the size, this is actually, when we're dealing with Modbus, everything is in words. So 2 bytes is 1 word. So our size is going to be 10, which is 10 words or 20 bytes. So first thing we'll do is open up the socket with the power supply. We'll flip that bit. And if we're successful, the output of the socket connect block will be true, which it is. And now we can hopefully get some data out of the power supply. So I'll flip this bit and we got it. So we read here, you can see in the read size, we got 10 words back, and the data that we got back is going to be populated into this word array that we have here. So if I go to my other watch tab, I'll add that word array so we can see the data. And there you can see we have, it's actually the exact same data we were getting over our Ethernet IP connection. We just got it over Modbus. So 23.8 volts is our current voltage on it. So I'll modify that and then I'll re-execute the block just so you can see the data change. Now we're at 24.2 volts. I just bumped the voltage up a little bit on it. So now we can still use structures in this since the read data is any. Now, I haven't tried this, so you guys will either see me fail miserably or I'll figure out something very convenient here. But I'm just going to use the same variable that I use for Ethernet IP since I'm not using it for Ethernet IP anymore. And I think I called it power supply EIP input. Obviously, it's no longer an EIP input. It's going to be a Modbus connection, but we'll try that. Because if that works, then it parses out the data automatically for us. Okay, yeah. So we do need to, it looks like we need to parse out the data afterward, but if you guys remember the trick we used for assigning the same address to two variables, that would work just fine for this. It is one additional step, but Modbus is a bit cumbersome to begin with, so that is Modbus as a client. A quick demo for reading registers as a client. Does anybody have any questions on that? Now you can obviously see that Ethernet IP is far more convenient. So is OPC UA, since we have to manage all of this ourselves. And if this socket were to drop off, we have to handle that properly. So there are other instructions we can use to monitor the status of this socket, and we can take corrective actions if we need to. We also need to sequence our reads, make sure that they were successful. So it is a bit more cumbersome, but there are still a lot of Modbus TCP devices out there. So I figured I would throw it in here. So that's Modbus as a client, or a master, it's commonly called. Now, Modbus as a server means we're essentially trading places. So we are now going to respond to clients that are asking us for data at a specific address. So for this one, there is a library included in the student material for it. So it's not a supported feature natively in our PLCs, but we do have libraries that work very well for it. So I'm just going to add a library to my project from the student material. Is it in here, maybe? There it is. Now, this library, the reason I included it is because it has a Modbus TCP server function block built into it. So I'm going to, well, I'll leave the client stuff there. That's fine. So I'll just add a new program and I'll stuff all of the Modbus server stuff in that program. Now in Modbus, there are essentially two types of data. So we have registers and we have coils. Coils are bits, registers are words. So if I mouse over these two inputs, we give it a variable of 1,025 words, an array of 1,025 words, and we give it a variable of 1,025 Boolean variables. So when we do this, index number 1 in our registers, for example, will be the value we respond to address 1 with. So this will make a bit more sense once I have a client running on my computer and we're changing data and seeing it update. But it will create the correct data type for us. So I'll call this MB regs for registers, and I'll call this MB coils for coils. So we need to do this because we're not an address-based PLC, but we need to respond to address-based requests. So like I said, address 1 is the first index of the array. Address 1000 is the 1000th index of the array, and the same applies to coils. So I will put some tags here just so you can see exactly what's going on with it. Okay. Don't have any errors, so I will transfer to the PLC. So what the Modbus server does now, once we enable it, is it opens up port 502 on our PLC for incoming socket communication. Now I've got a I have a client program on my computer that I'm going to be using to demonstrate this communication here. Give me a second to open it. There it is. So the piece of software I have open on my computer now is a Modbus client. My PLC is the server, my software on my PC is the client. So I'm going to start the server now. And nothing really happened because nobody is connected to me. So you'll see kind of in the background, when I connect to it with my Modbus client on my computer, you'll see this function block change. So I will tell it to connect to my PLC, which is 250.1, port 502, and I will hit OK. And if all goes as planned, you should see the function block in the background indicate a connection, which it did. So what these fields indicate on this block is this is the port that my laptop is connected to the PLC with. It doesn't really matter. It's just what we it's just what we reply to. It's not handled by our code that happens behind the scenes in the TCP stack. The IP address of the client, though, this is the IP address of my laptop. And it shows that we have an established connection. So everything looks good on the PLC. And we can actually use the output of this connected field here in our logic if we wanted to. There might be certain things we don't want to do unless we have a client connected to us, kind of thing. So this client software is polling all the time, and it's starting at address 1. It is asking for 100 words of data, and we're looking at coils currently. So I'm going to change that to holding registers. And now when I modify the contents of this Modbus registers, we should see those contents reflected in our Modbus client here. So I'll throw that variable in the watch tab so I can access the index members of the array. That was Modbus registers. And there are the 1,000 and some odd registers in our PLC. So I'm just going to enter some data. And we should see this data in our Modbus client, which there you can see. So FFFF, FFFF. Now there is an off by one scenario. If you use Modbus, you've probably encountered this. So address number address number 2 is FFFF, but index number 1 is FFFF. So we start at 0 in the PLC, we start at 1 in the client, and we always have to be cognizant of that offset. And I've seen this on many devices, the off by 1 thing in Modbus. So that's how we become a Modbus server with our PLCs. Now we can be a client and a server at the same time. So as you can see, my client or my server is running, we're exchanging data with my computer. And if I want to run the client at the same time and I want to double check that power supply data, just make sure my structure changed here. I didn't make it retentive. We can simultaneously be a client and a server at the same time. Except I have that structure in there, but let's do a quick online edit to fix that. Send our online edit. And now we're reading our power supply data while we're serving up data to another client over Modbus. So does that make sense to everybody? Everything Modbus that we've covered here, client versus server, the implementation, that kind of thing. Any questions on that? I guess I'll do a quick demo of the coils as well. So I'll put them in my watch tab and I will flip a few bits. And when I change the function code with my computer-based Modbus client, I should now get coils instead of holding registers. And you can see 0, 1, 0, 1, 0, 1, 0, 1. So the data that I flipped, the bits that I flipped in my PLC are coming in the coils now. So different function code. It doesn't tell you the function code in this software. Actually, it does, sorry. O2 is inputs. So I will disconnect my client, and you can see in the background that the connected output has gone false. So my application may want to behave a certain way when we lose a client over Modbus, and we can detect that with this function block. It's included in the student material, this library. So if you guys ever need to be a Modbus server down the road, you'll have this and as well as an example of how to implement it in the example program. Any questions before we move on? We're coming up on the home stretch here. Good. So kind of in summary here, OPC UA is very easy when you're a server. So we enable it, we publish the tags, and you're finished. Most of the setup work is done on the client side. So mapping the tags. In the case of security and encryption, there is a bit more work than what you saw today. We need to generate certificates, share certificates, and allow certificates on both sides. But yeah, if you ever need to do that, just call me. It's not that common. Now, Ethernet IP, setting up data links, fairly straightforward. You can incorporate structures into them to automatically parse that data out for you, like we did with our power supply. Explicit messaging, on the other hand, either tag-based or class instance attribute type explicit messaging, this is something we have to do in our logic, and we have to sequence and monitor the completion of, just like we would Modbus. Speaking of Modbus, as you saw, it is something we manually set up in our logic. We manage the connection, we control the polling, and we have to map that data. This is, from my experience, the way Modbus has always been on multiple platforms. A little more cumbersome, but very simple protocol, very well documented. So we've got 10 minutes left. So this is a chance if you have any communications specific questions, or if there's anything you'd like to see on the PLC from a communications standpoint, we might be able to demo that for you.
Do you guys have any EtherCAD documentation that we can get access to?
Loads of it, yeah. What in particular are you curious about?
I'm just starting out learning about it, and I'd just like to have a basic understanding before I start getting too deep into it.
Oh, okay. Yeah, I mean, we have a couple 600 page manuals on it, for
Perfect,
the deep dive of it. But
Can I just find those on the website?
yeah, so the ones, if you want to kind of stick to Sysmac, it's the NJ NX EtherCAT manual. And this is probably way too much information for you, but I think what you might be after would be maybe a higher level guide on what EtherCAT is.
Mm-hmm.
This will tell you, when it comes time to implement it on an NJ or an NX, exactly how we do it. But there are a lot of similarities with EtherCAT and Ethernet IP. So process data and SDO, service data communications. So process data communications on EtherCAT is very similar to what we set up with our implicit connection with our power supply. So this is data that's exchanged every cycle of the primary periodic task. And if we add an EtherCAT device to our project, you can see exactly what process data is being exchanged with it. So if I throw a servo drive on there, you can see exactly what's coming across right here. So this is our PDO map, our process data object map. So these are all of the registers that we're going to get every single communication cycle. They're also added to your IO map, so you can see them here. So it does kind of skip a step of having to pick a variable and map it to that connection.
Yeah.
Now, SDO messaging is very similar to what we did with the tag-based explicit messaging. So all the data in an EtherCAT device has an address, and we call it an index and a subindex. And we have a block that's very similar to the explicit messaging block if you needed to access a parameter that wasn't in the PDO map. Do you recall the kind of the demo we did on day one there?
Yeah. Yep.
Yeah. So I mean, from a initial setup perspective, it's super easy to set up. You auto detect your entire network. Everything has a node, a 1 byte node address instead of an IP address. So very easy to set up. And the data exchange happens, instead of being at an RPI, it happens at every period of your primary periodic task. So our PLCs are task-based, and by default, they have the primary task, and it's running at 2 milliseconds on my PLC. So every 2 milliseconds, we will have a complete data exchange with every device on the EtherCAT network. So yeah, I mean, as far as detailed specifics go, we've got the manual that outlines everything EtherCAT related in Omron.
Perfect. How do you guys deal with third-party EtherCAT devices? Like if I don't have a PDO from that third party?
Yeah, good question. So in EtherCAT, there's something called an ESI file. If you're familiar with EDS files on Ethernet IP, it's virtually the same thing, but for EtherCAT. So we can just right-click on our master, and we can go to Display ESI Library, and it will show you everything that you have installed. And I've got third-party stuff in here as well. And if you want to install a new one, pretty much every device should have a publicly available ESI file for it on the website. So you click on install file, you pick the ESI file, and it's added to your project. The vast majority of them that I've encountered work with Omron. Same with Ethernet IP, but there are always going to be some platforms that don't talk to every device, or some devices that don't talk to every single platform. But we are pretty good with third-party compatibility.
Okay. Cool. I just had we can talk later. I got a question for you after.
Yeah, sure. Yeah, I can stay on the call. One thing I didn't touch too much on EtherCAT is just kind of how it works. So we have a couple different topologies we can support. The most common topology is a linear network, a daisy chain, commonly called. So every EtherCAT device has two ports, an in port and an out port. You go from the master to the first in port, and then out the first device's out port to the next device's in port, and so on. With Ethernet IP, we would have to send a packet to each of these individually, often multiple packets, to get an update of their data. With EtherCAT, we basically send out one packet, and it has all the data that is going to the nodes in that packet, and it passes through the daisy chain, drops off that data at each of the device. Then the very last device flips that packet around, sends it back, and on its way back, the devices deposit their outbound data that has to go to the master into that packet, and it all arrives at once. So very efficient, very good for device level stuff. Now, we're not sending megabytes of data over the EtherCAT network, so it's good for device level stuff. It is limited in size, but very fast, very efficient. It happens at a predetermined interval. With Ethernet IP, the data gets there when it gets there. If it has to jump through a couple of switches, it might have to wait in line, which is why you've got this fairly big window in Ethernet IP of when that data can arrive before you start raising alarms for not getting that data. So, precision control, for example, in a motion application, EtherCAT is far better than Ethernet IP. But yeah, I will stay on the call after with you, and we can chat EtherCAT if you'd like.
Yeah, thank you.
Anyone else have any other questions on communications? Good. So before everyone jumps off, just a reminder, next week on Tuesday is what we're calling the open session. So if you've got something you'd like to know more about that we didn't cover in any of these sessions, feel free to come to that session and we can discuss it. If you're having any issues or questions with what we've covered so far, bring your project. Let's take a look at it. Let's see what happened. Let's fix it. And alternatively, we're going to also have most of our Western team on there. So if you have commercial questions or an application that you're planning on tackling in the near future here, we can also talk to find a good solution for you. So that is all of the content for the training portion of this. So thank you everyone who attended. Appreciate your time. And we hope